Hello everyone, welcome to the first video in the Advanced Database User and Developer series. This is a series I have wanted to make since a long time, I think since I started this channel, which already has been quite a few months ago. And the reason is I personally have a lot of experience with relational databases, and I think these are very important concepts which, if explained properly, are very simple, but can really improve the way we work with relational databases. And the first video, really, this topic could not have been different, and it must be about indexes, because indexes, if I had to name one feature which, if used properly, can really improve the user experience that we have with databases. So without further ado, let's jump to indexes in relational databases. And just to make a little advertisement for this video, here I am in the SQL developer. This we have heavily utilized in our series with basic SQL course for data analysts and data scientists. And there I linked a video where we did it. We created this test table. So it has an ID, which is a generated sequence. It has an X, Y, color, and fruit columns. So if we just take a look at the data, basically ID is generated from a sequence, upwards counting, X, Y are random numbers, and color and fruit are random strings, or not so random, but selected randomly from a list of possible values. Now, if I run this query on this table, and this table has 10 million rows, by the way, it fetched the results in 0.486 seconds, so like almost half a second, right? And if I just create a default index that you do very simple, you just do create index, and then let's say index test table ID on test table, and here ID. Now, this will take a few seconds to complete, and has been completed in almost 6 seconds. And if I now take this query, I change it to 300 to avoid caching the results, and I run this, we'll get the results in 0.016 of a second. So if you calculated the percentage increase in performance that we have got, this is incredible in my opinion. And basically in today's video, I will guide you through step by step, really from scratch, what a database index is. And as a bonus, I think, this question, what an index is in a relational database, is a commonly asked interview question. I personally ask it very often, and very rarely do I hear a correct response to this question. Okay, now let's jump to the theoretical part. So let's assume that we have a table. Now we just have a table, 4 columns, and we are interested in this column. So this is the column that we have just created index on, right? So we have executed just what we executed in the SQL developer, right? So the create index statement. What is happening in the background is the database is taking the data from the column and putting it in a separate data structure. And this will be a tree data structure. Now, in most cases, this will be a tree-like data structure, and this will be a B tree in most cases. So basically, a B tree stands for balanced tree. It is a tree-like data structure, and it's balanced because all the subtrees have the same height. So basically, from all the leaves to the top, you have the same height, right? This is a leaf, and this is a node. So these are nodes, and these are like special nodes called leaves. And this is a root of a tree. As we all know, in IT, trees grow downwards instead of upwards. So here, basically, we have our tree, and this is what the database is doing. It's physically taking the data and putting the data, the values from the column, in the tree. And then it's doing one more thing. It is also next to the value that it stores, so it takes the value from the column, it stores it in a tree here, and it also stores a pointer to the row on the disk. So the table in the database is saved on the disk. And when you want to retrieve the row, we need to perform what's called an IO operation. So essentially, we need to read this row from disk. And basically, we can store these pointers. These are very often called row IDs. So these are just like representation of a place where the row is stored on disk. So this is a very fast access method in a database. So basically it stores two things here in the node. It stores the value and it stores the pointer to a row. Now, in the actual B trees that are in the database, here we can have more than one value. I think in the example that I have here, we'll have only one values, but in a real database here, we can have more than one value. Speaking of examples, let's take a look at an example of how an index for such a column may look like. And here you can see this data like structure, so like a B tree, where we have the values, right? So basically we have all the values that we have in the column here in the tree. And we have the orange arrows, which represent the pointers to the rows, right? So 3 points to 3, 2 to 2, 1 to 1, and so on, 4 to 4 to 4, 5 to 5, 6 to 6. And basically now, if we want to look up for a row, what we would do in a standard table, let's take a 5 as an example, right? So what we would do is we would go from the top, we would check, read this row from disk, check the value, it's not 5. Read this one, check value, it's not 5. Read this one, check value, it's not. Here it's also not. And here we would read and we would find, okay, it's 5. So it has taken us, let's say, 5 units of time to perform this search operation, right? So here we found 5 after 5 units of time. And now let's try to do it with an index. How a search looks in such a data structure is, you start from the top always. You take this value and you compare it against what we want to find, right? So in this case, we want to find 5. And we are asking ourselves, okay, is 5 bigger or smaller than 3? In our case, it is bigger, therefore we go right. And this is how these types of trees are organized. If it's bigger, then it will be stored on the right. If it's lower, then it will be stored on the left. You can see here, like 2 is lower than 3, 1 is lower than 2, and here like 5 is higher than 3, and 4 is lower than 5, and 6 is higher than 6. 6 is higher than 5. And so let's continue our search. Let's go back to our search. We have 3 and we are looking for 5. So 5 is higher than 3, therefore we go right and we are at 5. So what we had to do? We had to compare our target against this. This is one operation. Compare our target against this. This is the second operation. And then to read the row, we need to go back right here. And this is the third operation, right? So we need to go back here, read the physical row. Therefore, it's 3 units of time, not 5. And we have the exact same results. And this is why indexes excel in improving the performance of queries, of lookups with like appropriate where conditions. And so once again, probably a real data structure that represents an index looks a little bit different, right? I already mentioned that it can have more than one value in a node. Actually, it can have many more values. And maybe in some databases also these here will be connected and the actual values would be repeated here at the bottom rows, but these, in my opinion, are all details, and these are not necessary if you actually don't want to go ahead and implement your own database engine. If you just want to be a good developer, a good DBA, in my opinion, this is sufficient what you have to understand. Now, let's take a look at an example where we actually want to add a row to the database, right? So we just do an insert, right? We insert a new value. Let's say this value will be 7. Now what happens is automatically the database will add this value to our tree, right? So here we have the row 7 and here we have the new rectangle which represents the value 7. And so in this case, basically it was added here like in the sort of empty space we had, which makes sense. Now I'm not claiming that this would be added like this, but what I want to say is that adding new values to the tree is relatively simple, right? So this is relatively simple for us, and I often hear this phrase that indexes slow down the performance of inserts. And I must say, this is true, because they do. However, I think they do it by so small margin that it's actually more true to say that they don't. Okay, maybe if you go crazy with the indexes and create very many indexes with very many columns, then maybe you'll start seeing an issue. But for inserts, this should not be an issue as far as I have seen. And so here in this case, right, this is like a relatively good spot for this. It satisfies still all the conditions, right? So we have the 7 is higher than 2, therefore it fits it fits right here. Now, the problem with this sort of is that these three, so adding 7 was simple, but if we had to add some other number, and then we had to do a reshuffle, or what is called a rebalancing of the tree, this could take a little bit longer. This is why database engines have like tons of features implemented around this to make this process as smooth as possible for the user. Okay, so we have already established that inserts are quite simple here. Now let's take a look at what happens if we want to actually delete a row. And this is more tricky. And essentially deleting and updating values in the index column, so in the column that is indexed, right? So in this column, this blue column in our case, it is more complex because it takes more effort to actually delete a value from an index or an update, right? An update is actually basically functions the same way. It's like a delete and insert. So here it takes more effort for us to delete this value from this tree, because let's say that we want to delete number 5, right? We delete number 5, and then we need to immediately rebalance the tree because it does not fulfill the deletion criteria, right? We need to probably, I don't know, move the 4 up here or do something like this. So essentially deleting records can be, and deleting and updating records can be a little bit trickier than actually inserting records, and the performance impact here may be slightly higher. Although still, if you are not going crazy with indexes, you are not creating 50 indexes on one table, or maybe 50 is a little bit too many. Let's say you are not doing like 10 indexes or 15 indexes on one table, and these indexes do not have 10 columns, because indexes can have more than one column, but to this we'll get. You should be fine. So here we want to delete 5, and we have deleted 5, and here an example, it's shifted, the 4 has been shifted upwards. Now I'm not claiming by these simple diagrams that this is exactly how indexes work, how B-tree indexes work, because there are also different indexes. However, once again, I think this is a good visual representation, a good logical representation of what happens. Okay, let's go back to our example here. Let's actually drop the index, and you drop the index by saying drop index test table ID, so basically the index name. You execute this and the index has been dropped, so that's good. And let's try to create a different index, because we already know that the index can be on one column, but we also can have an index on more columns. So essentially here I could say an ID and then say X, and I can also create such an index, which is on ID and on X. So now you can see that it has taken over 12 seconds, and it is dependent on the contents of the columns. And I must say this index is just a little bit pointless, because actually ID uniquely identifies a row, therefore you do not really need an X here. However, what I wanted to show you, right, is now that we have 2 columns in this index, if I make a query like this, once again, right, let's change it to 400. It is once again super fast, 0.01 second. Now I'll change this to an X, and let's see what happens. And once again we get 0.6, so this is as it was without an index. And the reason being is that if you have an index that is built on more than one column, you need to specify all the leftmost columns up until the column that you want to select. So here I have an X. So in order to use this X, I need here to specify ID equals, I don't know, 100 and X equals 400, right? And then I need to have an end here. And then it figured out very quickly that I don't have any results, because it's able to first search by the ID this value 100, right? So it does the comparison as we did with the number 5 example. So it takes this 100, finds the correct entry, or actually finds the correct entry, and then it checks, okay, this entry does not have X 400, therefore I return an empty set of results. So once again, you need to specify all the leftmost columns. Now, what does it mean that a query can use an index? So essentially, if we want to use an index with a query, we need to have a pretty simple where condition. In other words, like an equals, it's a simple where condition. If I do lower, let's do lower than 10, so that we get 10 rows. This is a simple where condition. You look like 0.01 of a second still, right? If I do bigger, it's also going to fetch us pretty quick, but it's going to fetch us only 50 rows because these are the settings applied by Visual Studio Code, but this would also work. But if I just did something like, I don't know, mod id for equals 1, right? So essentially the rest of division of the id by 4, and then I'm looking for equals 1, this would probably, okay, here it returns the results also pretty quick, but that's, in my opinion, due to the 50 rows cap. So if it had to actually go through all the table, it would most likely not use an index. And the same way is with character values. So here we have 2 character values like color and fruit. However, they have not that many unique values. So just because I know how the test data was inserted into them, basically they all have 4 unique values. And these are the cases of columns that you do not really want to index usually, because an index helps if it returns very few rows. So 1, 2, 3, 5, it's all fine, but now we have 10 million for unique values, so 2.5 million rows with each value. This is not something you want to use an index for. This is something where you want to consider partitioning, and to this we will definitely get in some future video. But in general, you have to keep in mind that an index created should return with a single value as few records as possible. If it can return 1, then it's great. Then it's getting into the primary key properties, right? And a primary key is nothing else than an index with some special properties like not null, and it's unique, right? So basically it enforces the unique constraint on a column. Now, in terms of how you can query, because of course you can create on character indexes on character columns, and essentially there you could query this the same way. So basically like with an equals, right? Something like is tricky. Some database engines support some queries with like if you have the beginning correct, some do not. But in general, in my experience, you would usually index numeric columns, and then if you index character columns, you essentially the only query that would be supported is just with an equals, right? So here smaller or bigger do not really make sense. One more, I would say, bonus part. So here, if we take a look at our query that we had right here, I essentially said to you, okay, I don't think it's using an index, and we actually don't have to think. We can check how the database is analyzing our query and how this is preparing a plan to execute it. But before we do so, let's execute the following query right here. So this we think should use an index. And then I go here in SQL Developer. If you, in any DBMS that you are using, if you just Google for explain plan, this is the keyword you are Googling, explain plan Oracle Postgres DB2. So in SQL Developer, I just click here and it shows me this graphical representation. You can also find it in basically in text, like in the system tables. But here we have a nice visual representation. Here we have like a table that shows us, okay, what are the options of accessing data in this object, right? And it says by index, row ID batched. We are looking for by index. You can also scroll down here, and here you can have this batch table access by row ID. And this is what you are looking for, right? And this is essentially the row ID also I mentioned, right? The part where it points to a row. You are looking for this. You are also looking for a cost of the query. So these are essentially the number of IO operations the database has to do, right? So this we also discussed. These are the units of time, so-called. And let's take this query, right? So this is a cost of 4, and here we have the index access. And let's actually execute, or we don't have to execute it. We just need to click here. What we see here is full, and the cost jumped to 13,000, which is a lot, right? which is a lot. I mean, it's not super a lot when it comes to the cost that the database queries can have, but it's definitely more than 4. It's significantly more than 4. But it's also slightly different query. So let's maybe do something simple, right? Let's have on y equals y, and y is just a numeric column. So here you can see it has like some rows with 1. It's not unique, but let's generate an explain plan for this, right? An explained plan for this, like this query has 13,000 cost. And what you are looking for, what is a red flag, I mean, it is acceptable, you can do it. However, you want to avoid it if you want good performance, is this full access method. So essentially, if you scroll down here, you can also see the full right here. So it tells you that the database performs so-called full table scan. This is essentially what I begin the example with, right? So it goes row by row, it takes the value 1, reads first row, checks if it's equal to 1. If not, then it takes another. If not, another. It has to go through the whole table to look for these values. And if there was an index on this column, this would be much, much quicker. Let's maybe do one more example, right? I will just drop the index. I will create an index just on the X column. Or better off, I'll create an index on the Y column. Let's check it out. So if you remember, there we had 13,000 cost, the query cost essentially in the explain plan. Now it has taken us 6 seconds. Let's now take a look how big of a cost this is. And here you can see 19. So essentially here also you can see this interesting fact that the indexes should return you as few records as possible. And yeah, just because I know it, so the X is almost unique. So essentially it generates you a value between 0 and 10 million, and you have 10 million rows, right? So like on average, there should be 1 row with 1 value. And here, this Y is not really unique. It generates values from 0 to 1 million. Therefore, we had like on average 10 rows for every value, right? Which I think even is true for Y equals 1, right? I think here we have 14, so not exactly true. But going back to the explained plan, here we have a cost of 19 versus the cost of 13,000, which is much, much less. So that's it for the indexes. This is a convoluted topic. I think it gets more and more interesting and more difficult very quickly once you start going into all the options that it has. But essentially, I would recommend you to open, for example, the Oracle page on the create index and just look how many different options there are. This gets quite overwhelming, but I think this level of understanding that I have provided you in this video, and I think it was surprisingly short, is sufficient definitely to be a good database developer and also to be a decent DBA. This would be sufficient. So for now, I'd like to thank you all for watching. If you have any specific topics that you'd like me to talk about, that you have always wondered about, please put them in the comments. I will definitely make a video about explain plans because I find them super useful and basically a great leap forward in terms of how efficient you are in using a database. But if you have any other suggestions, please put them in the comments. And thank you for watching this video, and I will see you in the next one.